Hi everyone, it's Miss Lenorovitz, and in this video I'm going to do a short introduction to more energetic math number 2. In this problem set, you're going to be working with units of power and energy and oftentimes converting between them, as well as then doing some calculations to understand costs. So all of the work that you're going to be doing in this problem set can be done with dimensional analysis. As always, you want to make sure you're showing all of your work and all of your units. And dimensional analysis is a really good tool to use to make sure you're organizing your work and coming up with a plan that will get you an accurate answer. So this problem, I'm going to go through problems 1 and 2 in this video. Once you have gone through those, feel free to give these a try on your own or to rewind and play back. So as you work through this problem set beyond questions 1 and 2, the remaining questions are all going to be some variations and applications of what happens in number 1 and 2. So if you can do numbers 1 and 2, you can do all of these other ones. It's just a little bit further application. The only piece that's a little bit new is capacity factor when you get to question number 9, but there's a definition there, and I think if you read that carefully and be patient with yourself, you're going to be able to figure that out. All right, so let's take a look at problem number 1 to start. All right, problem number 1 asks if the basic charge for electricity is 0.0683 dollars per kilowatt hour, or in other words, 6.83 cents per kilowatt hour, how much will it cost per year to run a 60-watt porch light for 8 hours per day, every day per year? All right, so we have a lot of different units here, and it's helpful to tease out what they all represent. So the first one that comes up is a cost in dollars per kilowatt hour. The second one that comes up is 60 watts. The third that comes up is 8 hours per day. And then the last thing that we need to pay attention to is what we're trying to solve for. So we want to solve for how much is it going to cost. So we want our final answer to end up in dollars. Let's do a little review of what these units actually represent. So let's start off with 60 watts here. So 60 watts is actually a measure of power. You may recall when we're thinking about electrical power or demand, we're talking about how much electricity is required to do something. So our basic unit there is going to be watts. So you can think about how much work, for example, do these ants need to put into place in order to lift this apple. So that's our first measurement there. This other value, the 6.83 cents per kilowatt hour, the top part is familiar to you. That's a representation of money. But the bottom part of that fraction, kilowatt hours, is actually a representation of energy. So you may recall from class that when we're thinking about electrical energy or use, we're talking about how long we're asking that power to be used. So we have watt hours. In this particular problem, it's kilowatt hours. So we also want to pay attention to the prefix there. Remember that kilo means 1,000. All right, so how do we approach this problem? Let's take a look at this. When you're doing dimensional analysis, you may choose a slightly different starting spot than I did. Remember that you're going to be doing multiplication, so the order of operation is less important. I started out by using this value, the 60 watts. So that's our unit of power in this case. I know that ultimately I want to get to dollars. So one of the things I'm going to need to do in order to do that is I'm going to need to convert from watts into kilowatts, and eventually from kilowatts into kilowatt hours. So the first step that I chose to take here is to multiply the conversion factor of 1 kilowatt is equal to 1,000 watts. So now my answer is going to be in kilowatts. I know from the problem that I'm going to be operating this light 8 hours every day. So that's my next conversion factor here. And I'm going to be doing that every single day for a year. So there are 365 days in the year. So now when I go back through, I can cancel out watts in my numerator and denominator. I can cancel out days in my numerator and denominator. And the units I'll be left with will be kilowatt hours per year. And that's actually where I want to be on my way to solving my problem. It's not going to get me all the way there because I want to end up in dollars, but it's going to get me part of the way there. So I went ahead and multiplied across the top. So 60 times 1 kilowatt times 8 hours times 365. And that got me 175,200 kilowatts. On the bottom, what I'm left with is 1,000 times years. So I have 1,000 years at the bottom. What I'm going to do next is just simplify this fraction, and I apologize, I left off an important part of the answer here in my in-process answer. So that becomes 175.2 kilowatt hours, and I really should have that over years here. I'm then going to take that answer and I'm bringing it down here. I could continue in one long line with this if I wanted to. I'm not done yet because I know that I want to figure out how much it will cost per year. So if I know that I need 175.2 kilowatt hours, I'm now going to put in my cost per kilowatt hour. So in this case, it's $0.0683 per kilowatt hour. So over a year, I'm going to need to spend $11.97. So that's how you solve number one. All right, in problem number two, I'm asked how much energy in kilojoules does a 75-watt light bulb use when it is turned on for 25 minutes? So again, we're starting in units of power, but we want to get to units of energy, and specifically energy in kilojoules. So we know that energy is equal to power times time. Other thing that we need to pay attention to here is we're starting in watts, but we want to end up in joules. So this is where this conversion at the top is going to be helpful for you. A watt, by definition, is 1 joule per second, or 1 joule over 1 second. So how do we go about solving this one? Well, the first thing I want to think through again is the fact that energy is equal to power times time. The other thing that I wrote down for myself as a helpful reference here is that 1 watt is equal to 1 joule per second, or a joule over a second is equal to 1 watt. So when you are putting together a conversion unit for this, a joule over a watt second is a pretty simple way to convert. The other thing that you can do, knowing that 1 watt is equal to a joule over a second, is you can go ahead and just replace anywhere that you see watt with joule over second. So let's take a look at the solution here. We've got to start with the value that we've been given. So we know we have power of 75 watts. We know that it's going to be on for 25 minutes. Now, minutes are helpful. Those are definitely a unit of time, but it's going to be helpful for us to convert that time into seconds. And the reason for that is we know that a watt is equal to a joule second. So if we can convert our time into seconds, we'll be able to isolate our power into our energy into joules. And then from joules, we can convert to kilojoules. So I took my power, 75 watts, times my time, 25 minutes. And then my first conversion factor that I put in is that there are 60 seconds in every minute. That again allows me to convert from minutes to seconds. I'm then going to use the conversion factor that 1 watt is equal to a joule every second. So I can cancel out my units of watts, and I'm left with joules on the top and seconds on the bottom. Now I can see that my watts and my seconds can actually cancel out. The last step that I need to take is, now that my answer is going to be in joules, I actually want to get it to kilojoules. So here I just need one more conversion factor. 1 kilojoule is equal to 1,000 joules. Now I'm going to go back and just simplify. I'm going to multiply across the top. 75 times 25 times 60 kilojoules on the top. On the bottom, I have 1 times 1 times 1,000. When I go ahead and finish that mathematical calculation, I end up with 112.5 kilojoules. So hopefully that gives you an idea on how to start these problems. Again, each of the other problems is going to be a variation or combination or application of these ideas. And as you're working on these problem sets, remember it's going to be helpful to refer back to the conversions at the top here. I also encourage you to refer back to the notes that we took in class. And I also encourage you to look back at the energy, power, and usage handout. As well, you will see that I've also linked another informational video that will just help you get a little more clarity potentially about energy and power, and the units that are used for those two. So good luck. I look forward to seeing what you come up with.